Okay, thank you, Marcy. And thank you everyone for joining us. We appreciate that you've taken time out of your busy day to join us and learn more about wood and the 2018 NDS changes. And this presentation is registered with AIA, for those of you that are seeking AIA credit. Hopefully most of you or all of you have downloaded a PDF of the presentation. I know Brian had provided that link in the chat box. It is available. And for those, this is the course description, and then we have the learning objectives. We'll look at the NDS changes in the 2018 NDS, and we'll also look at some of the impacts of what the changes are in the ASCE 716, and more importantly, the fasteners that are used in wood and how the wind loads affect the fastener design and nail design, and specifically related to design of nails for withdrawal and head pull through to resist the new wind loads. So just a little bit of background regarding the NDS. This is originally developed back in 1944 with USDA Forest Products Lab. And as you can see through the various years, the introduction of new provisions, we are now on the 2018. The previous version was the 2015, and one thing you might note is that the wind and seismic provisions were not updated in the 2018. It was, however, updated in the 2015 version, and then previous to that was the 2008. And some of you may be aware or not that AWC is the ANSI accredited standards develop of the standards, and we do this via the Wood Design Standards Committee. Now that Wood Design Standards Committee consists of people of various backgrounds, different stakeholders, and they're all very dedicated to creating this standard. And it's some really great people on that committee. So the 2018 NDS is referenced in the IBC and IRC, which are now available for purchase on the ICC website. And then this goes over some of the major changes that have occurred, well, the primary changes that have occurred in the 2018 NDS. One is the reference to ASCE 716, where we go to get our design values or design loads. And then we have the added equations for withdrawal design values for smooth shank, stainless steel nails, and provisions for roof sheathing ring shank nails, accordance with ASTM F1 1667. New design provisions for roof sheathing, fastener head pull through, and then methods for calculating lateral design values for threaded nails, and revised timber rivet design values in the tables, and then some new terminology, or actually revised terminology, related to fire design for wood members. And then lastly, the NDS supplement design value updates. So that gives you a little bit of an overview of this. And then just to give you an overview of the actual publication, we have the first 3 chapters of the general chapters that apply to generally every wood product. And then we have the special products chapters, which is sawn lumber all the way up to cross-laminated timber, which was new to the 2015 NDS. And then we have the connections chapters, mechanical connectors, dowel type fasteners, and split rings, shear plates, and timber rivets. And then lastly, the special loading conditions and fire design for wood members. But right here at chapter 11 and 12, that's where the majority of the changes are in the NDS. And this is where Buddy will take over in the presentation when we get into chapter 12. Now, and this slide also denotes that the chapters that have no changes. So if you wanted a brief overview, this designates those chapters with no changes. But we're going to go through and proceed through each of the chapters just to get a review for some of you that haven't used the NDS in recent times. And then we have the appendices, where the only major change is the title for chapter or Appendix L, which has been simplified to state typical dimensions for dowel type fasteners and washers. That was the only change to the appendices, major change. And then we get into the supplement, which Buddy will go into more detail, but we've had some changes related to some reference design values for sawn lumber, MSR, and MEL, and then the non-North American sawn lumber and structural glue laminated timbers. Now, in Chapter 1, this applies to all wood products, and the change that we have here is the reference to ASCE 716 for minimum loads standard. I'm getting a message here. I don't know why. Okay, and then some notations that have been added. We have revised some notations and some new notations. The new notations are all of them. The revised notations are the effective char depth and the nonlinear char depth have been revised, and Buddy will get into that in more detail. So the EI effective, the GA effective, which is the effective bending stiffness and the effective shear stiffness, are new notations, which I'll explain later in the presentation. And then the DH and the WH and the WH prime and the TSN, let me get this, are all related to the addition of the fastener head pull through. And then the A char, A effective char, and then the nonlinear char rate are all related to the timber related to the fire protection design. So that's just to give you an overview to show you we don't reference it here, but it'll let you give you some background on where these notations are used within the publication. So getting into Chapter 2, which is the design values for structural members, we have some minor change or clarification actually, and this is just with any product that we use related to designing the structure, is that the engineer or the designer needs to know what the end use of that structure is and needs to make account for this in our design. So as a clarification of that, we have updated the language within the section on responsible of design to adjust for condition use. Is we've added to clarify that the designer needs to adjust for the conditions of use, and to clarify that the designer is responsible for determining the appropriate design value adjustments to use for end use conditions that are addressed in NDS. And so just clarifying that it's the designer's responsibility to understand and accommodate for this. And we've added this little graphic just to, again, add a little humor on how exciting these standard changes are when we deal with them. Okay, also for the load duration factor, we've clarified that the load duration factor for, that says C sub D, for impact, the 2.0 impact load, does not apply to wood structural panel. And this is just a reflection of what the industry recommends. That's just shown here. And then Chapter 3, we get into the design provisions and equations. And we've clarified some requirements related to when we're checking the beam stability and determining the beam stability factor, C sub L. We've revised F sub B star, which is the reference bending design value multiplied by all applicable adjustment factors except for the flat use factor, the volume factor, and the beam stability factor. So we've clarified that the volume factor shall be included in the calculations of F sub B star when CV is greater than 1, which could be in the case where you're using structural composite lumber. So let me repeat this so it's clear. When determining F sub B star, you include all applicable adjustment factors except the volume factor, the flat use factor, and the beam stability factor. And that is the case. The exclusion of the volume factor is when C sub V is less than or equal to 1. And if C sub V is greater than 1, then it needs to be included in determining this F sub B star factor. Now we have a poll question, Marcy.
Yes, we do. The 2018 references which of the following codes are standards? The 2018 IBC, the 2018 IRC, the ASCE 716, or all of the above? Great, 50% have already voted. And we're only 25 seconds in. So I'm going to close this at 80%, and we are already there. So, and I'm going to go ahead and share the results. So let me see. 60% say all of the above. 37% say ASCE 716. 3% say 2018 IBC, and none say the IRC. So I'm going to give this back to you, Michelle, for the real answer.
Thank you. And the real answer is ASCE 716. Now, we did talk about the 2018 IRC and IBC, but those two publications or building codes reference the NDS. It's not the other way around. The NDS references ASCE 716. Thank you very much. Okay, now on to chapter 4, where we're dealing with sawn lumber. Sawn lumber, we have some changes related to flat use factor, and this has to do with just a clarification on the application of the flat use factor in that it applies to beams and stringers. So just some clarification of the language. Then we get into the incising factor. And the incising factor has this table which has some minimum requirements for utilizing this table. And one is that the maximum depth of the incising parallel to grain needs to be 0.4. The maximum length needs to be 3/8 inch. And then the density of the incising is 1100 per square feet. Now we've added some language to accommodate or to have an alternative use of determining the incising factor, and that it needs to be, it would be obtained from the company providing the incising factor, provided that the incising patterns and lumber sizes, that they are per a specific incising pattern and lumber sizes. And so they would obtain the incising factor from the company providing the incising. So just an alternate way of obtaining the incising factor than from this table. And then just a clarification for wood trusses, it's been revised to clarify that the buckling stiffness factor, C sub T, for wood trusses applies not only to plywood, but also to OSB, or in general, wood structural panels or wood structural sheathing, to include OSB. Previously, it just said plywood. Okay, on to glue laminated timber, structural glue laminated timber. And we've had a revision related to the, excuse me, the, I'm trying to get this, sorry, the radial tension. Now, radial tension is specific to glue laminated timber beam. There's also radial compression specific to glue laminated timber beam, but it has to do with when you see, look in this picture where they're curving the actual glue laminated timber, and there can be some tension, radial tension and radial compression. Well, there's a clarification in the footnote that references that also when you're looking at the radial tension, that there needs to be an inclusion of the adjustment factor for wet service and as well as temperature factor. So this is just a clarification to show that those applicable factors apply when looking at radial tension. And it had to do with, in table, the general chapter, chapter 2, it wasn't specifically noted in table 2.3.3, which is the temperature factor, and then it doesn't include it also in the section 5.3.3 for moisture. They don't specifically reference the radiotension. So now it specifically states it in the adjustment factor table for glue laminated timber. Okay, on to chapter 6. We have no changes there, but just as a reminder, the chapter 6 just does cover round timber poles and piles. And then the chapter 7, no change there. It's prefabricated wood I-joists. And then chapter 8 has to do with structural composite lumber. If you recall, in 2015 version, we did add LSL and OSL to the structural composite lumber. There has been some clarification of the language related to the service conditions, and that's in section 8.1.4, which talks about the reference design values reflect dry service conditions where the moisture content is of sawn lumber in service is less than 16% moisture content. So the term sawn lumber was added to this to clarify, and it's in reference to ASTM D5456, which uses this as a benchmark for structural composite lumber. And it also uses it for I-joists as well, the benchmark for the moisture content. So if it causes some puzzle, this minor change, this just gives you some background by the introduction of why it's stating sawn lumber in the structure composite lumber chapter, because that's the way it is referenced in the ASTM D5456. And we've also, let me go back to this. We've also added some language or clarification related to the volume factor. Now, you noticed here, here it is, the volume factor applies to bending when you're calculating the bending, but now it also applies to the tension here. So new is the volume factor related regarding tension, and it was to correlate with, again, ASTM 5456. So that's added related to the standards, ASTM standards. And another minor change has to do with this I for the footnotes, referencing the footnotes. It used to be up in the column, but since we added this volume factor for the tension parallel to grain, we had to clarify that it only applies, the footnote I only applies to the bending. And that just has to do with determining the volume factor versus the beam stability factor, that they're there's a difference between the two and they're not combined. There's some criteria for that. Okay, chapter 9, there's no change related to the wood structural panel chapter. And then chapter 10, where we had some changes related to cross-laminated timber. If you're aware of it, into the 2015 NDS, that's where we added cross-laminated timber to the 2015 NDS, and that was also included in the 2015 IBC, International Building Code. And we've had some clarification here related to if you're doing LRFD design, where now we have, instead of having a conversion factor of 2.88, it's been changed to 2.00. And this is to be consistent. There was a change related to ASTM D5457, and to that, related to that change, to be consistent with that change. And that ASTM 5457 is the standard specification for computing reference resistance of wood-based materials and structural connections for wood and for LRFD design. So to be consistent with that. And we've also had some revisions related to CLT deflection provisions to include the term of EI, which is the effective EI, for effective bending stiffness, and then GA, which effective, which is the effective shear stiffness of cross-laminated timber. And this is to correlate with the changes that you will see in ANSI APA PRG 320, which is the 2017 version of the performance rated standard for CLT. And then the revisions to this actual equation was to be had to do with being consistent with that standard and developing the EI, which is the apparent bending stiffness, related to the apparent building stiffness. So chapter 11, this is where we get into the bulk of the changes that have occurred. And there were some revisions related to the connection design provisions, which were primarily in response to the significant increases in components and cladding roofed wind designs in ASTM 716. Wind uplift related changes include new fastener withdrawal and new fastener head pull-through design provisions, which Buddy will go into in more detail. But we've had to include a provision for fasteners with round heads, and there's a clarification or the adjustment factors for the connections to add head pull-through. And then also when we're dealing with wet service use factors, we've added also provisions related to the moisture content and pull through also for those fasteners, specifically to distinguish between roof sheathing ring shank nail, that's RS, and then post frame ring shank nails from other types of nails. Okay, then we have the second, or actually third poll.
Absolutely. So let's see, we have the volume factor C sub V for structural composite lumber shall be included in the calculation of F sub V. Is that true or false? All right, we've got about 50% have voted. You all are on top of the game today and voting quickly. I appreciate that. So, all right, I've got 75% in the effort of time. I'm going to go ahead and close and share the answer. So we have about even split. 54% are true, 46% say false, and the real answer, Michelle.
And the real answer is false. And this has to do with structural composite lumber. It applies to bending and it applies to tension parallel to grain. Okay, and then we're going to hand it off to Buddy.
Yeah, can one of you send it to me? I'm having trouble here. I apologize. It's not prompting me to share my screen.
Well, it has you as presenter.
Yeah, okay, so you're seeing my screen now. Good, good, good. All right, so we're going to pick up here on chapter 12 and continue along with the discussion of changes. So
Buddy, we're
I'm not seeing your screen. I think we'll take it back and then we'll give it back to you.
Okay.
So let me take it back and then I'm going to give it back to you. Okay.
Sorry,
so
folks.
Try this.
Hang in there with us. There it is.
Okay.
Oh, I took the wrong screen. Let me change it.
There we go.
All right. My apologies. Chapter 12. The biggest change here has to do with the addition of roof sheathing ring shank nails. And so as we walk through some of the changes to ASCE 716, I think you'll get a sense of why we introduced this new fastener and some of the new provisions that go along with that. So let's talk a little bit about nails. The nails that you see in the NDS are based on ASTM F1667, as Michelle has mentioned a couple of times already. There are provisions for what are called power-driven fasteners in various evaluation reports. One of those is through ICC called ESR 1539, and that deals with power-driven fasteners like the ones shown here on the screen. So we're going to talk a little bit about properties of those nails. One of the first things that we'll deal with has to do with the head diameter and how it's configured. So again, for ASTM nails, it's going to be pretty much concentric round head above the shaft of the nail. They can be offset for the nail guns like you see here in this figure, D-head or notched head nails. And we start talking about new provisions for head pull-through. Note that you would be able to accommodate these fasteners as well with those head pull-through provisions. You just need to calculate what that head diameter or the area of that head, I guess, that would be resisting pull-through. So we'll talk about that when we look at the example in a little bit. The other thing that's important when we're talking about withdrawal is the makeup of the shank. Typical nails, box, common, and sinkers in the NDS are going to have a smooth shank. We've got ring shank nails as shown here in the second graphic and kind of blown up here at the bottom of the slide. We've got the helically threaded or screw threaded type nails, and then barbed type nails as well. And so that's important to know. Then we got different tip configurations, if you will. And the important thing here is that the length of the nail for both lateral and withdrawal includes the tip, but when you're calculating lateral capacity, for example, you need to exclude half of that tapered tip. And so it's one of the things you need to be aware of, and why we show in the appendix for the geometry of the nail what that tip length looks like. So here are a couple of examples of the configurations that we show in Appendix L of the NDS, L4 for the common box and sinker nails, L5 for the post-frame ring shank nails, which was introduced in either the 12 or the 15 edition of the NDS, and then the new roof sheathing ring shank nails. So the text incorporates enabling language for those roof sheathing ring shank nails. Note also that we've added a line saying that nails used in engineered construction shall meet the supplementary requirements of ASTM F1667 S1 nail bending yield strength. And so knowing more about the bending yield strength of the nails is an important consideration for engineered applications. Head diameters are important, and then again this new Appendix L6, Table L6 for the roof sheathing ring shank nails. The other thing that's important here is the thread length, TL, as defined in this drawing. And so when we get to an example here in a little bit, you're going to need to remember that the withdrawal values for these ring shank nails is based on the thread length, not the length, the full length of the nail. So keep that in mind as we move forward as well. Again, some more enabling language here for smooth shank nails. This applies to the bright or galvanized carbon steel nails. We've also added provisions for stainless steel nails or spikes. And these new provisions have to do with revised withdrawal design values for stainless steel nails. You'll notice the existing equation in the NDS, W equals 1380 G to the 5/2 D. The new equation for stainless steel nails, 12.2-4, is 465 G to the 3/2 times the diameter. So that's a brand new equation. I'll show you a graphic here in a little bit of some test data that shows the difference between those two. Here, how the design values pan out. We've added a couple of additional diameters here in table 12.2C to pick up some additional diameters for these carbon steel nails. You notice that we've dropped off the right side over here the threaded nails that were in previous versions of the standard. And so that's because we're more clearly defining ring shank nails as the ones that have that higher design capacity. And so what you see here with footnote 3 is for the deformed shank nails of equivalent diameter to this table, you're going to use the withdrawal design value here. So that's really a reduction of about 10% for what we used to call threaded nails. But in place of that now, well, let me just cover the stainless steel nails. So table 12.2D then incorporates those withdrawal values for stainless steel nails. And so I'm going to jump ahead here, apologize for this, but I wanted to give you a sense. If you look ahead in your PDF at slide 50, that's where I'm going to jump to real quick to show you the difference between the carbon steel nail withdrawal values and the stainless steel nail withdrawal values. These are ASD withdrawal strengths for 8-penny common nails. This is pretty indicative of the rest of the fasteners. The reduction here you see for Southern Pine of G of 0.55 is pretty substantial for these stainless steel versus carbon steel bright or galvanized nails. So that's what necessitated the change in the NDS and development of that additional table to cover stainless steel withdrawal values. So back to slide 48 then is where we'll pick up again. Jumped out of order a little bit, but I'm on slide 48 now, where again we've introduced some enabling language for the roof sheathing ring shank nails and talk about those withdrawal design values for those. So then we get to table 12.2E, which in previous versions of the NDS just included the post frame ring shank nails. Now we've added withdrawal capacities for the roof sheathing ring shank nails, and so those are tabulated here inside the box. We're going to show you a design example here in a second, so just hang in there, but you've got the design equation and the tabulated values to choose from based on this is just an excerpt of those different specific gravity values. So these are only applicable to roof sheathing ring shank nails or post frame ring shank nails meeting the ASTM F1667 standard. So again, that's where we've kind of dropped out that what we used to call a threaded nail, a deformed shank nail, those helically threaded nails and others that aren't really defined yet by F1667. So as we get more data, we may be able to bring those back, but that's what we have for now. And so we already talked about that. I'll keep on going, and we'll talk about then the new design provisions for the 2018 NDS dealing with fastener head pull-through. So just jump over here to the right-hand column, look at the equation W sub H, and this is for a side member thickness, a net side member thickness less than 2.5D. The equation is 690 pi d sub h is the fastener head diameter. G squared is a specific gravity, and then T sub NS is the net side member thickness. So those are the properties you need to determine head pull-through of the fastener. And I'll point out this very last sentence over here in the bottom of the second column. Pull-through for other materials shall be determined in accordance with 11.1.1.3. That takes us back to what we talked about earlier with the power-driven fasteners. If you can determine the area of the head based on the configuration, then you can determine those head pull-through values for those other fasteners as well. But this obviously with pi d assumes a circular head on the fastener. So then in addition to the equations, we've tabulated the values here based on the net side member thickness, head diameters. You can see the values here, and these are unadjusted values just like the withdrawal values, but these are the head pull-through values. So let's look at an example. That's probably the easiest way to get a handle on what does this look like with these new provisions. So the fastener uplift capacity on something like what we're showing here in this drawing, where you've got wind uplift on some wood structural panel sheathing, is going to be the lesser of the withdrawal capacity and the head pull-through capacity. So we're going to check both of those to see which controls. So slide 54, we're looking at what's given here for fastener uplift capacity. We're going to look at a 0.131 by 3 inch roof sheathing ring shank nail, RSRS nail, and I need to give a shout out to Lori for pulling this example together for us in MathCAD. But this is a Doug Fir large 2x6 with 7/16 OSB side member. And so the specific gravity is 0.5 for both the lumber and the OSB. The length of the nail is 3 inches, as we showed in the assumptions there. Diameter 0.131 for the shank, a head diameter of 0.281. But then the thread length, come back to thread length versus nail length, is 1.5 inches. So we jump to the next slide. Remember, we're going to use thread length for this withdrawal calculation. The net side member thickness ends up being 0.4375. We either enter that into the equation here that we showed a little bit earlier for withdrawal capacity. It gives us a value of 59 pounds per inch. That's the value you could also pull out of table 12.2E, 59 pounds per inch. Then times the TL, which is the thread length, not the nail length, takes us from 59 to 88 pounds of withdrawal capacity. So that's what we've had up until now. That was it for the design. But since we've increased the withdrawal capacities of some of these nails, that creates perhaps a weak link with head pull-through. So now we've got new provisions to check fastener head pull-through. So continuing the example with the net side member thickness, we're going to calculate a head diameter, and so or calculated 2.5 times the head diameter to figure out which equation to use. So we end up using equation 12.2-6A and calculate a head pull-through capacity of 67 pounds. Now, this is an unadjusted capacity, right? So, I mean, you could adjust this by the wind load duration factor of 1.6, adjust the withdrawal capacity times 1.6 and compare them that way. Probably, I mean, it's an apples to apples comparison if you just were to do an unadjusted capacity comparison. And we see here that the head pull through in this particular case actually controls. So that 67 pounds is then what you could use to adjust by all the other adjustment factors, including load duration of 1.6. So that takes us to this table, which we've excerpted from the 2018 Wood Frame Construction Manual, Table 3.10. And if you come back next month in January, we're going to be doing an overview of the 2018 Wood Frame Construction Manual. And what you see here is that we've tabulated fastener uplift capacities by taking the lesser of, per footnote 2, withdrawal versus fastener head pull through. And so this table, this value here for 7/16, 0.49 is pretty close to what we saw for the 0.5 example that we just did a little bit earlier for Doug Fir. And you come down here for that ring shank nail, it's about 106 pounds. I think with Doug Fir, you actually get 107 pounds if you apply the load duration factor of 1.6, which is what's incorporated in this table for wind design in the wood frame construction manual. So this gives you a little bit of a sense of the difference in capacities between 8-penny common, 10-penny common, and these roof sheathing ring shank nails. Now look here at this column that we just talked about. Notice that the 10-penny box nails actually have a higher capacity. That's because fastener head pull through is what's controlling these new roof sheathing ring shank nails in this particular example. So that's why we introduced both of those into the new NDS, where you're checking both withdrawal and fastener head pull through. So I'm going to stop there and have Marcy come back and lead us in another poll.
Absolutely. All right, let me launch it. Calculating fastener head pull through requires which of the following properties? All right. Fastener head diameter, net side member thickness, side member specific gravity, all of the above, or answers A and C only. All right. Probably give you about 20 more seconds. I've got about 70% have voted. And I'm going to go ahead and close the poll and share it. All right, so 67% have said all of the above, 29% answers A and C only, and then just a little tiny smattering for fastener head diameter and net side member thickness. All right, and Buddy, I'm gonna send it back to you to tell us the real answer.
Okay, so the real answer is all of the above. And so if you go back and look at that head pull through equation, you're going to see that it included head diameter, net side member thickness, and specific gravity in the equation. So 2/3 of you are paying attention. And so let's move then to ASCE 716 and talk a little bit about some of the wind load changes. You may have already seen this if you've been looking at ASCE 7, maybe not. So in general, what you're going to see, and this map is a basic wind speed map for risk category 2 buildings and other structures. Generally speaking, and this is a wind speed map, so I want to distinguish between wind speeds and wind pressures, which we'll talk about in a little bit. But you're going to see a decrease in the wind speeds along the New England Northeast coast up here, top right of the U.S. No changes to the coastline from North Carolina to Texas until you start to get inland here, where some of these contours transition over to non-tropical storm controlling areas. Oops, sorry. No change to the islands, Hawaii, Puerto Rico. But over here, notice on the West Coast, a lot of the wind speeds have gone down. Not a lot of change out here in the Midwest to the wind speed. So the wind speeds changes in some parts of the country are actually going to offset some of the increased roof pressures, which is what we're going to talk about next. So here we're seeing a typical CNC load diagram from ASCE 7, shows all the different zones 1, 2, and 3 for the roof, which is kind of what we're focusing on here. Those new roof pressure coefficients are increasing. So along the hurricane coastlines, you're going to see some increases. New England, where the pressures the wind speeds went down. Out west, where they went down, you're not going to see those increases because they're going to be offset by some of those wind speed maps and elevation factors. So along the hurricane regions of the coast is really where we're going to start to see some of those pretty significant increases in wind loads. And here's a table that gives an example of the CNC roof coefficients, including internal pressures. And so we've got roof slopes from 7 to 20, 20 to 27, 27 to 45, all the different zones here. And over here in zone 1, which is an interior zone, you can see 100% increase in roof pressures on the interior of the structure. And so pretty significant changes, pretty significant increases. So one of the reasons, one of the options that you have to offset those increases and make sure we can keep the sheathing on the roof are roof sheathing ring shank nails. And so that's, let's take a look at a couple more examples here just to kind of get a sense of where will that help you? What are some practical ways that this might come in handy for you in the design process? So let's look at 110 mile per hour exposure B. That covers a pretty good chunk of the country, interior US maybe. And so let's say we've got the 7/16 wood structural panel sheathing, specific gravity 0.42, 24-inch rafter spacing. So if we're looking at zones 2 and 3, our roof sheathing ring shank nails would require a 6 and 12 nail spacing. So 6 inches along the perimeter of the sheathing, 12 inches in the field. Whereas an 8-penny common would require a 6 and 6 nail pattern. So now we got to go 6 inches on center in the interior of the panel. And again, this is at the perimeter, zones 2 and 3, but the interior of the panels here in these perimeter zones would require a 6-inch nail spacing, whereas the roof sheathing ring shank nails you could get by with 6 and 12 on the whole roof system. So it gives a simpler nailing schedule option for the entire roof. You don't have to do anything different at the perimeter of the building. What about some of the higher exposures? So here's let's look at a hurricane zone, 180 miles per hour exposure B. Now we're probably going to need thicker wood structural panel sheathing. I think this is around 5/8 in 1930 seconds. Specific gravity of 0.55, rafter spacing 24 inches. So let's look at a complex roof like the one pictured here, where it's kind of hard to tell where the edge zones and interior zones leave off and pick up. So one easy way to deal with this would be to use the roof sheathing ring shank nails along the perimeter of the roof. It would require a 6 and 6 nailing pattern. The interior you could get by with 6 and 12 on the interior of the panels, but again, pretty simple to just specify 6 and 6 on the entire roof, and that's it. You're done. 180 mile per hour roof system now with a 6 and 6 nailing schedule simplifies everything. So again, a couple of practical ways that might help you in those hurricane zones. I'm just going to go ahead and get on through the remaining slides here and make sure we leave some time for Q&A. But this is kind of where we're crossing the T's and dotting the I's. 12.3.7 talks about dowel diameter for smooth shank nails and deformed shank nails. So we're going to use that D for not the root diameter, but the shank diameter, the main diameter for both smooth shank and deformed shank nails. So what does that mean for our lateral values? Table 12Q has not changed except for adding roof sheathing ring shank nails. So this is to determine our lateral design value Z for wood structural panel side members. And you see we've added a column here with the designation for the roof sheathing ring shank nails based on a certain diameter. These are your lateral capacities. So pretty straightforward changes here. Obviously bigger change with respect to withdrawal capacities, but the lateral capacities in this case, we've got a specific gravity of 0.42 versus 0.5, which we showed in the previous slide. So we've got design values for that. Now we get to the post frame ring shank nail design values. And so we've revised those slightly because of a change in the bending yield strength, or a better information, I guess, about the bending yield strength of those post frame ring shank nails. So you'll see just a slight decrease in the values here for post frame ring shank nails because of that. Same for the table that includes a steel side plate versus a wood side plate. Just a slight decrease in some of the values here based on decreased bending yield strength for those nails. Chapter 13, no changes to the standard. Chapter 14, just a fairly minor change of how we tabulate timber rivet design values, where we limit the maximum distance perpendicular to grain between the outermost rows to 12 inches. And so you see we've had to truncate these tables. I think they used to go out to about 20 rows or something like that. And so to be consistent with other provisions of this chapter that limit that distance to 12 inches, we've truncated these tables. And same here with limiting the rivets per row for these timber rivets. Not used a whole lot, but if you are using those, please note those changes. No change to chapter 15. Then we get into chapter 16. There were some clarifications here that we want to just briefly touch on, having to do with fire design of wood members. So I want to look at this diagram real quick before we jump into the discussion, because of the methodology. The dotted line here, represents the original member before a fire application. The sort of squiggly line here represents the char layer. And then I want you to take note of this heated zone and the rounded edges. Okay, so we're going to talk about char depth and effective char depth. And so this heated zone means that the effective char depth is accounting for some strength loss in this heated zone and some of the rounding that occurs on these types of members. So this slide basically depicts the clarifications that we've made between char depth and effective char depth. And it's probably easier to see here in this table, 16.2.1a for the effective char depth. And let's talk about this for a second, because that effective char depth, A sub EFF, is what's used in structural fire design. So we assume a char rate of 1.5 inches per hour for wood, both lumber and glulam. That's been proven over and over again based on testing. So if we're doing if we're using wood in a non-structural application, say to protect a rim board from the inside, or to protect some connectors like we'll talk about here in a second, assuming a char depth of 1.5 inches per hour for non-structural applications is certainly legit, because we're not worrying about that particular member, that sacrificial piece of lumber or blocking charring away after an hour. But for structural applications, we are wanting that wood structural member to continue carrying the load. So this effective char depth accounts for that heated zone, the rounding, things that occur that will affect the strength of the wood member. So that's that's always been the case, but we're trying to further clarify it for designers to understand exactly how this methodology works. Same for section 16.3, where we've clarified that wood connections, including the connectors, fasteners, and portions of wood members, shall be protected from fire exposure for the required fire resistance time. So here's an example over here on the right of a test that was done not too long ago. In fact, Woodworks just had a webinar yesterday or the day before on this, where one of their fire protection engineers, or one of the fire protection engineers named David Barber that was involved in the testing, talked about some of these test results on connectors and how you need to protect the steel with enough either wood, fire-rated gypsum, or other approved material to make sure that the fasteners hold up during the expected exposure. All right, got a couple minutes left here, and we will wrap up at the top of the hour, but then stick around afterwards for some Q&A. So don't worry if you have to leave, it's all going to be recorded, but hang in there if you want to pick up some additional time for Q&A after the top of the hour. So the appendix tables, again, updated to include head diameter for fasteners, new roof sheathing ring shank nails. I'll just run through these quickly. NDS supplement was updated, not a lot of revisions to traditional lumber. There are a couple of new revised grades of MSR and MEL. Redwood was simplified pretty significantly by removing any grades that require close grain, so that looks more like just the other species of softwood lumber now as far as number 1, number 2, number 3 grades. Norway spruce from Norway is added to the foreign species table, and then some new modulus of elasticity values for glulam for shear-free modulus of elasticity values were added. So Marcy, I'm going to skip this poll question because we're right up against the top of the hour here, but the nominal char rate, if you were paying attention, assume for lumber and other mass timber products, is 1.5 inches per hour. That's the nominal char rate. The other thing we'll point to, and maybe show you here in a second after we close, is a paper that we've written to detail all the changes that have occurred. When you go to our website, you can see a link to those paper under the What's Changed button to get more details on these changes. So I'm going to stop there, have Marcy come back and close us out, and then we'll do some Q&A.
Sounds good. Oh, I just lost my controls. Here we go. All right, let me take the screen back. Are you seeing my screen?
Not yet.
Why are we having some issues with this?
I'm not sure. I'm going to try and
here we
send it
go.
to you and see. Did that work?
Now, do you see it?
Yep, we're good.
All right. Sorry about that, folks. All right. So thank you, guys. Great presentation. And I bet you can't hear me because I had my microphone up. Just a quick information, as usual, our partner organization, Woodworks, provides wood project assistance and other resources. If you want to reach out to them, email help@woodworks.org or visit their website at woodworks.org. works.org and then /project assistance. You can also request assistance from them on our survey. We have a page for that. All right, also, in order to help design professionals stay informed about technical issues affecting the wood industry, we offer a design professional membership. There are many benefits, including discounts on publications. Go to our website and the membership page if you're interested there. We also have code official connections benefits for qualifying code officials. And as you can see on this slide, there are many benefits for those code officials with that program. Then following today's webinar, give us about 30 to 40 minutes, and we're going to send out an email, complete the survey for a chance to win a free publication. There's a link for that survey. Check out information about your certificate of completion and CEUs. Note that you're not going to immediately get that certificate or CEUs. You'll get that probably within 2 weeks of today. Also remember that in order to get that, you must have been present for 90% of the 60-minute webinar. That's 54 minutes. Also, please join us again on January 18th for our webinar on 2018 WFCM. And we are hosting that for 2 times, one in the morning and one in the afternoon, because it's a very popular topic and we are maxing out our capacity. So if you have any other questions or want information, just email us at education@awc.org or visit us at www.awc.org. All right, thanks again for your attention, and now back to Buddy and Michelle for questions.
Will C sub V be the same for structural composite lumber products when we have them in bending and tension, or will C sub V vary depending on if it's bending or tension?
All right, great question. Michelle, here's the
Yeah,
slide
that's a good
for you.
question. In the NDS, we reference that the user should see the manufacturer for the C sub V. And I'm not sure if it would be the same or different. It depends on what you get from the manufacturer. I don't know if you know what, Buddy.
No, I don't. So it's going to
Yeah.
be manufacturer specific, and look at their evaluation reports to see how they handle that.
Right. Okay.
I see a question here about 2018 NDS, where it's referenced in the 2018 IBC and 2018 IRC, so we'll reinforce that. That's where it's referenced in the brand new building codes. What else you got, Lori?
I'm just scrolling through here. We have a lot of questions today.
Let me get back to the stainless steel graph because I saw a question about that.
Was one I was just about to ask. So why is it that the stainless steel capacities are less for withdrawal?
Yeah, I think, I mean, if you have worked with stainless steel, anything, you know that there's just not a lot of friction there. And so when we've got galvanized and box nails and those types of finishes, you're just going to have a whole lot more friction between the fastener and the wood member. And so these tests that were done certainly bear that out, that stainless steel just does not have the friction that you see to adhere to the wood that we see with brighter galvanized common nails.
That's a reflection of the finish of the nail, right?
Mm-hmm. Yeah.
Another question came in. Can I jump in?
Go ahead. Yep.
Related to the MathCAD design examples. Are those available? And are there other resources?
Lori, why don't you take that one?
Yeah, the withdrawal and nail pull head pull through example for today that we did is going to be part of the example problem document that's going to be coming out with the 2018 NDS early next year. So we don't make our MathCAD sheets available for download, but you will see that that example problem included in that document, which we're hoping will be available when the hard copies of the NDS are available sometime early next year.
Yeah, and that's a good segue to talk about when that availability will happen, sometime first quarter. Here's the web page on our website that you're seeing now on your screen for the 2018 NDS. And so from here, you can download what we call a free view only copy of the NDS and the NDS supplement. So you can't print these yet. We're working on commentaries, and so first quarter sometime, once we get that finished up, then we'll make available PDFs that can be printed and book and comment. You can add comments and that type of thing to the PDF, and then we'll get printed copies out as well. So sometime first quarter, keep an eye on this website for those changes. I'll jump to the NDS here that's online just so you can see. You can navigate with bookmarks and that type of thing. So it's all there and something you can take a look at. The paper that we talked about, I'll go back to the web page here where you click on what's changed. That will get you to this paper that we reference in the presentation that goes into more detail about the changes to the 2018 NDS. And so I know the browsers or your screen's kind of catching up, but that's what the paper looks like. So, Michelle, Lori, anything else?
I think that's good. We're coming up on 3:10 here, so I don't know how much longer we want to keep folks.
All right. Let me do one more thing, and I'll refer to a paper that ISANTA put together, and I'll have Brian throw that link in the chat box for you. But a couple of our engineers here worked with ISANTA to help them. That's the International Staple and Nail Tool Association that developed that ESR 1539 standard or evaluation report that we referenced earlier. And we tried to help them put together a technical advisory document here that walks through some of these changes that have been made to withdrawal values and the ring shank, roof sheathing nails, the post frame nails. So the link in your chat box, or if you just go to the ISANTA website and do a search, you should be able to find this document that provides some pretty good background on a lot of those changes that occurred. So I think we'll wrap up there, and thank you all for being here, and we wish you a very happy holiday in the next few weeks, and hopefully we'll see you again in January for our 2018 Wood Frame Construction Manual webinar. Have a good day.